So let's see if we can finish today this chapter. I lost one of my notes. That is bad. Here they are.
Okay,
So
if you can lose your nose, it's legit for us to hand in like problem sets.
So let me finish this section that it was essentially at the very end. So remember our problem: we were in Minkowski spacetime. We had an accelerated observer in the x-t plane with some acceleration a. We were able to build from him a system of reference in the whole right wedge. So we have the right Riddler observer, system of reference. We did the same with the left Riddler observer. Then we did quantum field theory. We were able to build two different quantizations of a scalar field. The standard Minkowski one that we saw in chapter 2, and now a new one which is putting together the two quantizations that these two system of references build. The question is that we know that there is a preferred vacuum in the standard Minkowski representation, the Minkowski vacuum. The question is, how is this vacuum represented in the Hilbert space of one of the observers? So in order to do that, we use this technique of Bogoliubov coefficient, and we were obtaining that this Minkowski spacetime, when we express here, is given by a quite non-trivial state, which is given by a product on all frequencies and all transversal momentum of a sum from 0 to infinity of this factor n pi omega over a, where a is the acceleration of the reference observer in that system of reference. And then we had this quite funny, or quite remarkable, if you will, correlations between Riddler quanta, Riddler particles in the right and left wedge. And I was emphasizing that it shows quite non-trivially, that the Minkowski vacuum is made of precise correlations between things here and here, which are causally disconnected. We already knew that a vacuum state is always something global. So by nature, quantum essays are global. They have correlations between the space-like separated points. So we knew that from chapter 2. But this shows that quite explicitly. The next step was take this state, and so this is a state in the tensor product state. So have some parts from the right and some parts from the left. The next step was to project it on the right part. So the way of doing that was, the standard techniques in quantum mechanics, not even quantum field theory, quantum mechanics, is to build a density matrix from this guy, which is a pure state, but we can build a density matrix from it. So this has the same information as this guy. And now we want to take trace. This is like a matrix in that Hilbert space, and we want to take a partial trace, a trace on the degrees of freedom of this guy. So take a basis from this guy and compute the trace, and whatever is left is a matrix only on that space, and is what we are looking for. So taking trace on the left Hilbert space, we obtain what we call the Unruh right density matrix, which I showed to you, that is precisely given by e to the minus the Riddler Hamiltonian over 1 over kappa t, so kappa no, KUTB over z, where z is just the trace of that rho, and that is precisely a thermal state, a thermal density matrix when the temperature, what we call the Unruh temperature, is proportional to the acceleration in the appropriate units. And this is what we call the Unruh effect. This is quite a remarkable result, that the standard Minkowski vacuum, when restricted to the right Riller wedge is indistinguishable from a thermal state, so from a blank body state at that temperature, where the temperature is proportional to the acceleration. And now I wanted to finish this section. This is where I stopped last day, so I want to finish this section just making some comments on that. So to me, this derivation is the most systematic one, because you really obtain the full state, which is this density matrix, and from that state you can get the information that you want. What is normal, more normal in books, is to find the computation of the expectation value of the number of particles operator. But I can obtain that from here. So from here, that is just a step. I can obtain that, and I can obtain much more. So just to tell you what normally you find in books, for instance, we can now compute the average number of quanta, of Riller quanta, Riller type quanta with frequency omega and transverse momentum. Okay, so we take the Riller particle number operator for modes with frequency omega and transverse momentum k, and we want to compute the expectation value. So we want to compute its expectation value in that state. So when you have a density matrix, the expectation value is given by the trace of rho times the operator. So this is the computation that one has to do. The expectation value of this state, of this thermal state. And as we know, from previous chapters, this is just given by the sum of the beta coefficients squared. So if we know the beta coefficients, this is going to be just the sum over. I don't have to either sum over anything because so I don't even have to sum over anything because I am just restricted to one frequency. And so if you do the computation, you would obtain a h bar omega, if you want, omega over, so with h bar over kappa t unroot minus 1, as expected from a thermal state. So the number of, I may have an integral there over all, so I may have an integral there, sorry. I may have an integral here over all transverse momentum. Square this way doesn't appear there. But what we obtain is that the number of particles with frequency omega just follows the Planck law, as we can expect from a thermal state.
So we are not fixing K1.
Sorry?
We are not fixing K or transverse.
Right, it's just particles with frequency omega.
We can remove that and K.
Yeah. And this, I think it was obtained for the first time by Davis in the 75. And normally, this is many times the way of showing the Unruh effect, computing this number. But you may have also a state which is not thermal, but the number operator happens to be the same as a thermal state. So this by itself doesn't prove rigorously that the state is thermal. We have, on the other hand, obtained the density matrix, which tells us that the state is thermal, period, and now you can compute moments of that density matrix. The number operator, the product of two number operators, of 3 or 4, whatever you want to obtain, and the results are going to be always thermal. So now just a couple of comments. to close this section. The first comment is that, you know, what we have derived here is that, you know, if you ask the inertial Minkowski observer what is the state, he would say it's the vacuum. However, if you ask the accelerated system of reference, he could tell you that no, that the state is full of particles. In fact, you know, this is, you go and you measure particles with this spectrum. So this seems like a paradox. This may seem a paradox. I mean, we have discussed this already, so I will not emphasize that a lot. So do you think it's a paradox? No, it's not a paradox. You know,
What's the paradox?
The fact that the Minkowski inertial observer, if you ask him how many particles for you is in the Minkowski vacuum, he would say 0, it's the vacuum. But in the same state, if you ask the accelerated observer, he could say that, you know, as many as this is full of particles with thermal spectrum. So they will disagree completely in statements involving how many particles there are in the state. And my statement is that this may seem a paradox, this, you know, this contrast of statements. But it is not a paradox, because we have learned that, you know, that the notion of particle is basis dependent. You know, I like to use, so just the period is, there is no paradox. Because the notion of particle, as we have emphasized many times, is basis dependent. So they have just different notions of particle, different definitions of particle, dependent.
Okay, so I have a question about that.
Okay.
Suppose you have a brick, and it is built out of atoms that are built out of particles that are, you know, is the notion of what your brick is basis dependent, or is this just
a brick is quite big, so it's not quantum at all. But you think about what an electron is. An electron is not a ball that is around your atom. No, it's a wave function. You know, it's given by some quantum mechanical wave function, and you can extract particle-like properties from it. And this is what you call a particle, and you make this intuitive picture of a ball. But this, you know, it's not a ball at all. You know, it's just you know, the notion of one electron depends on how you are defining the electron. In Minkowski spacetime, there is a preferred notion of electron, given by the time-like symmetry, but in general, there is no. So people would disagree on how many electrons there are in a quantum state. And this is a very good example.
The charge, if you have more electrons in the
No, but
charge,
you have also positrons, and the electric charge will be 0.
So this is even at the level of atoms?
I mean, doing a quantum field theory of atoms, the atom is not a fundamental particle, so the
No,
question
it's not.
But if you do an effective field theory with atoms, that would be also true, and you quantize them. You know, and you know, next section we'll be doing the same with particle detectors. I think show that clearly to you. And the goal of this chapter is just, you know, that this example to me is really shocking. That you know, you just have to accept it because you know it's the way it is. And
Like, what
so
are these particles? I mean, like, these are bosons, but like among known particles, do these come into that category, or?
say it again.
Like, we know particles, right? I mean, like types of particles, like bosons, fermions. In bosons, we have different, and in fermions. So, in which category? Like, these are bosons.
This is a boson with spin 0.
Okay.
But they can do the
It's
same
boson?
exercise with electrons. I would obtain, because they are fermions, with a plus here. But I can do the same with photons, and with photons I will obtain the same, with a factor 2 because 2 polarizations. But this is, I mean,
Okay, so when we say that, like, in universe we have these many, like, there is some count, right? Like, people say that 10 raised to the power something, like this is the number of atoms or particles in universe. So that is like, that is false then. I mean, like, we cannot say how the number of particles in universe.
that is ambiguous.
Yeah.
In this room, yes, because we have a preferred definition, but in the cosmological level, there is no. So let's hold the discussion for the end of the next section. So the analogy that I like to give with this is, you know, is even in special or general relativity. So forget about quantum mechanics. So if you ask an inertial observer or an accelerated observer, what is the time interval between two events in a space-time. You have two events, event 1, event 2, and you ask the inertial observer, he will tell you they are separated by delta t and by delta x. And you ask the accelerated observer, he will tell you these two events are separated by delta tau, which is different from delta t, and delta x, delta psi, which is different from delta. Do you think that's a paradox? No, you use a different system of coordinates. Coordinates doesn't mean anything. Of course, if you ask them what is the distance between the 2 points, they will agree. Exactly the same happens in quantum field theory. If you ask them something which is basis dependent, they will not agree. If you ask them what is the energy momentum tensor on that state on any of these points, they will both agree. It's exactly 0. If you ask them what is the correlation function, they will agree. That is a state independent. That is the same as a distance between 2 points. But if you agree, what is the time interval, the delta y, delta z between two different events, they will disagree, as they will disagree in the amount of particles that there are in the state. So this is exactly at the same level. And the last comment is that I want to make, just in preparation for the Hawking effect, is that the Minkowski vacuum is a pure state. And the answer to this question is trivial, but I want to make it anyway. Now, the state that we are ending at, this delta U, the Unruh in the right Rayleigh weight, is a mixed state. We know that quantum mechanics, by time evolution, can, if the quantum mechanics is unitary, maps time evolution, pure states in pure states. Do you think this is a violation of unitarity of the quantum mechanics? So the fact that we started with the Minkowski vacuum, and now I ended up with a state which is a mixed state, and somebody
have traced out
right, I am just, this is a mixed state because I am not considering the whole Minkowski vacuum. The right Rayleigh guy doesn't have access to the information on this side. So he's losing information on the Minkowski state. So a pure state for him looks a mixed state just because he's losing part of the information. There is no, there is nothing wrong about quantum mechanics here. So it's just, if you are twin, you have a brother like you, and I'm not watching the other one, you are the only one. So I am missing information here. So there is nothing wrong with quantum mechanics. The only happens is that the Rayleigh observer doesn't have access to the left Rayleigh wedge. So
is there any analogy between black hole information paradox and this?
Of course.
So what is that?
This is out of the black hole. This is inside of the black hole. So if you are, and the initial vacuum is defined everywhere. So if you are out, you cannot see what happens inside. There are correlations that you are losing, and therefore the state looks mixed to you.
Yeah. So where is paradox then?
We will discuss that.
Okay.
We will discuss that. So I am just saying this because it's very similar to what happens in the black hole case, there is an additional subtlety, which is, here, obviously, there is no paradox. There, I will tell you why, a paradox may arise. Okay. I close this section here, so I think it's quite clear what happens. The result is very clean. And now I'm going to go to the last section in the chapter, with title section 4, a uniform accelerated detector in Minkowski spacetime. So the goal of this section is complement and support the results of previous section. And perhaps perhaps what I'm going to do is to ask the same question, but in a more physical way. Because you have these two quantizations, one state in one, you project on the other, you can still say, okay, these two notions of quanta are kind of mathematical, I am not fully convinced. In addition, we had mathematical subtleties, because remember that the two quantizations were unitarily inequivalent. So you may still be unconvinced of the physical result. And in fact, people were unconvinced. And in 1976, 1 year after all these results, Unruh derived what I'm going to do in this section. And the effect is called Unruh effect because that derivation, that physical picture of what the mathematical computation they did, was what really convinced people that this is a real physical effect and not a mathematical artifact of using inequivalent representations or something like that. So here, the question I want to ask. So this is again the same, but in much more physical terms. Is what a uniformly accelerated detector could observe particle detector if the quantum field is in the Minkowski vacuum. This is the question I want to ask. We know how to do that. In chapter 4, we had a section about particle detectors when you have a stationary spacetime and you have a detector following the trajectory of a time-like symmetry. It has a well-defined definition of particle. That detector can be used to measure the amount of particles that we have. And we, in fact, derive in detail what is the response, the probability of excitation and the excitation of a detector. Note that here, no Riller focus space. So I only will have one focus space. So only standard Minkowski quantum field theory, QFT, and a detector coupled to it. So if you want, mathematically it's much cleaner. I only have one standard familiar representation and a particle detector coupled to it as we did in chapter 4. So what you can do is go to your notes on section 2.5. So this applies. All what we did there applies. Again, remember that what we had there was a detector following a trajectory in space-time, and was very important that that trajectory is a time-like symmetry of the metric. But note that the accelerated trajectory is also in technical terms, is also a killing trajectory, a time-like. In other words, if you stay at that curve, the Minkowski metric doesn't change to you. We saw that because, remember that the Riller metric in Riller coordinates was static. So the coefficients of the metric in Riller coordinates doesn't depend on time. So that means that, if you are a Riller observer at a constant Riller coordinate, the metric is stationary. So you are really following the killing trajectory. In Minkowski you have many killing trajectories. Any of these curves are killing trajectories, and the killing vector field here is partial t Minkowski time. We are following a different killing trajectory, which is partial tau, which is a different It's also a killing trajectory. In fact, this is what boosts generate in Minkowski spacetime. So all what we did there applies here because our detector will in fact follow this trajectory, which is a time-like symmetry of the spacetime. So all the math that we did there apply. So go to section 0.5, and there we computed the total probability at first order in perturbations of transition between, remember we had a detector with two energy levels, so I want the detector to go from the initial one state, can be the ground state or the excited, well, can be any of the two, to the other state, let me call it final, where final and initial both can be the ground or the excited. The state of the field is any arbitrary state, alpha, and here I am summing over any final state of the field. I don't care what is the final state of the field because I only care if the detector gets excited or emits quanta. That probability was given by the following formula. I am just copying from chapter 4, 1 over h bar squared. G squared is the coupling constant. We now have a matrix element which has to do with the details of your detector. You know, your detector may have some properties, and this has the information of your detector, so it's not really relevant depending on the detector. Let me call this MIF, so I don't have to write this all the time. And now the important part, remember, was an integral dt plus dt minus e to the I over h bar I minus EF t minus multiplying the 2-point function of the field I need more space, so let me start with the 2-point function here. The 2-point function of the field, where the 2 points are evaluated along the trajectory. So, 2-point function of the field evaluated along the trajectory of the detector. So it's an integral along the trajectory. Let me tell you what was t minus, t plus, and t there, because this was true for any state of the field and any trajectory. So t, in that case, is the proper time along the trajectory. T plus was T1 plus T2, T minus T1 minus T2, and the state 2 is the excited, and the state E1 of the detector, these are energies of the detector, this is the ground state. And x of t is the detector trajectory. I should use a different letter because in this chapter I was using t for the Minkowski time, the inertial time. Here t is really the proper time along the trajectory, so I should use tau. That in the chapter 4. For the accelerated detector, I will use tau. So this t is like a generic proper time along a generic trajectory. So also in this section, I will put the mass of the field equal to 0 for simplicity. just because otherwise it gets too long, because expressions are not so clean. But the results hold exactly the same for the massive case. The only thing is that I am lazy, so what I want to do is to use this general expression for our case. Put alpha to be the Minkowski vacuum, and the trajectory to be a uniformly accelerated trajectory, and compute what are the probability of excitation and de-excitation.
What was mu again?
Mu, the mass of the field. So mu is remember, mass of, the mass is really, mu is mass over h bar. So the goal now is to apply this. So I should keep a number here. I don't remember which number I was in. Let me just start from scratch. So the goal is apply this equation 1 with alpha to be the Minkowski vacuum and the trajectory in a uniformly accelerated trajectory. And this is the goal of this section. But before, as a warm-up, let's do it for an inertial trajectory. For an inertial trajectory. So you have the state is the Minkowski state, and I have a detector in my hand, and I am just inertial observer. So I want to know what my detector will measure. Of course, you know what the result is. It's going to measure nothing, because the vacuum is the same as the vacuum, but it would be interesting to see what is the probability of excitation and of de-excitation. Remember also that in chapter 4, I told you that many times this two-point function only depends on the difference between T1 and T2. It only depends on T minus. And then the T plus integral, nothing depends on T plus in that case, and the T plus integral can be just removed, and you can compute the probability per unit time. This is what is going to happen here in the two cases. But this expression is more general, just in case you cannot do that. So let's do first the inertial observer. What do I need here? I need the trajectory. The trajectory, the proper time now is the inertial time. If I choose appropriate coordinates, the trajectory is just t, 0, 0, 0. I put the detector in my origin of coordinates. That is the detector. I also need the two-point function in Minkowski spacetime in general. And then I need to write it when the 2 points belong to the trajectory. So let me first write the two-point function in general in Minkowski spacetime for any 2 points, x and x prime. And after that, I will evaluate it on the trajectory. And this is why I choose a massless field, because this expression is just simpler. So it's proportional to h bar, and it's just minus T1 minus T2 sorry, I forgot to add. Let me do it here because my back is going to kill. So the two-point function in Minkowski spacetime in the Minkowski vacuum is just h bar over 4 pi squared, and now you have minus the geodesic distance squared. The only thing is that we need a minus I epsilon, because the two-point function is a distribution rather than a function. x1 minus x2 squared. Oh, sorry. Let me just put here the 3 coordinates. x1 minus x2 squared. So quite simple. 1 over the geodesic distance squared with the I epsilon because it's a distribution. So really, here always explicitly one has the limit when epsilon goes to 0 from above. And I insist this is needed because the two-point function is a distribution, so you need to give this I epsilon, which is what provides the appropriate distributional set. So now,
So I'm confused. If this is a massless particle, how can you choose an inertial frame where its x, y, and z coordinates don't depend on time?
no, the field is massless, and the quanta of the field will follow, null rays. But the detector has a mass. This is the trajectory of the detector.
Oh,
Myself,
okay.
I am just with the detector in my hand, and I am still. And I am not massless, believe me. So what we need is the projection on the trajectory. So to write this two-point function when the 2 points belong to the trajectory. But that is trivial. So I need the first point in the trajectory, so x of t1, where x of t is the trajectory, x of t2. So the only thing I have to do is to... There is always the limit, but I don't write it anymore. So this is the projection on the trajectory trivially. Okay, I have all the ingredients that I know I need to compute what I want. So let me start computing. Any question about this?
Why is there a minus sign?
It was here also.
Right, but why is there a minus sign there in the first place?
Here?
Yeah.
It's the geodesic distance, and we are using the signature minus plus plus plus. So it's minus
Okay.
minus time interval squared plus space time interval squared.
I guess where does that first equation come from?
This is the two-point function in Minkowski space-time, so you can I think I wrote it in chapter 2 for
I'll just look back.
the massive case. So the two-point function of any field, you just decompose the field as a sum in modes. You write the field as a sum of modes A plus conjugated a dagger, and this is just, if you do the math, this is just this mode. This one evaluated at this point, and this one evaluated at this point. So it's a summing mode. And modes here are trivial, are into the I kx minus omega t. So it's just a summing mode. It's go to chapter 2 and it's explicit.
Okay.
Very standard computation. So what I want to start computing is the excitation of an inertial detector. So I want to apply that expression when I go from the ground state to the excited state. Just copying what I have from there. Integral in plus, integral in minus, e to the plus, e to the I, e1 minus e2 over h bar t minus, times the two-point function. The two-point function is just this one. H bar 4 pi squared t1 minus t2 minus I epsilon squared. This is t minus, as I told you that it was going to be. The two-point function only depends between the difference of the 2 points. So the integral in t plus is by itself. In principle, if the detector is on forever, will diverge. But what we want to do is to just divide by that integral and compute the probability rate, the probability per unit time. So this is probability rate. Which is just removing that integral. So essentially, it's like the Fourier transform of the two-point function. T minus E epsilon. So this is the integral we have to do.
What happened with the minus sign?
I forgot it. Minus there. Thank you. Thank you. And this integral is quite easy to do because, you know, if you remember your complex calculus, what we have to do here is imagine that I analytically continue this to the complex T minus, complex plane T minus. So T minus is the variable, and what I have is an integral on T minus from infinity to plus infinity. I have here an exponential, but the exponent, because E1 is bigger, is smaller than E2, this is smaller than 0, so this is negative. So I know that you know what I can do is use Cauchy theorem. This is negative, so this is like minus I positive t. So if I close the circuit on minus I going to infinity, this exponential will be 0. So there is no contribution from here, and I know that the whole integral is given by the sum of the residuals of the poles enclosed by the contour. So let me call that C, that contour C. I do it in this way. So all I have to do is to see how many poles this integrand has on that, and sum the what do you say?
Residue?
Say it again.
Residue, I think?
Residue, that thing. Let's call it oranges. But you see, if you see this function, there is only one pole, which is when t is equal plus I epsilon. So the only pole is here, I epsilon. So no poles there, this integral is 0. So choose the contour, contour, so choose C. As expected. So an inertial observer, an inertial detector in the Minkowski vacuum doesn't see anything because the state is a vacuum, there are no particles to detect, as we could expect. Let me now, so is that clear for everybody? Let me now, for curiosity, compute the probability of de-excitation or emission. So probability rate of de-excitation of an inertial detector. So doing exactly the same, let me just write directly the probability rate, going to be 1 over h bar squared g m2 1, but they are symmetric, so it doesn't matter. dt minus from infinity to infinity, e to the I. The only difference is that now we have e2 minus e1, t minus, and the same two-point function. T minus I squared. Is the result going to be 0 now? Now the exponent is positive, is the difference. So we can use Cauchy theorem, but we have to close the path on the bottom part, and we have orange there. So we have a pole there. So it's going to be non-zero, as expected, because if you have a detector excited in Minkowski spacetime, it will decay spontaneously. So if you compute, this is going to be minus 2 pi I minus, because the way that one is closing the circuit, the sum over residues enclosed by the circuit. So if you I think in this case it's plus the 2 H bar, one of them cancels, and we have G squared, the matrix element that depends on your detector, and if you do it, we have H bar. This is the result. Now I have a number. So if I call this equation 2 corresponds to the probability rate of spontaneous emission or de-excitation of a detector. So as we expect, and you go to the lab and you measure the probability rate of the excitation of an atom, and that agrees with that. So this supports the picture that the Minkowski vacuum is in fact absent of particles, of inertial particles. I didn't give any name to that equation, so let me call this equation 2, and then I change the number 3. And what I want to say is 2 plus 3 tell us that the Minkowski vacuum is empty of inertial particles. Now I want to do something more interesting. I want to take the same detector. So don't change your apparatus, but put it in a trajectory which is uniformly accelerated. So before that, so now we put the same detector, so the same apparatus, in a uniformly accelerated trajectory. So first, remember that the trajectory, let me call it just tau. The tau is the proper time along the trajectory, which agrees with the Riller time. The trajectory is an hyperbola. As we saw at the beginning. And the acceleration is in the x direction, so y and z are just in the origin of coordinates. So this is the trajectory. I also need the 2-point function along the trajectory to do the computation along the trajectory. So all I have to do now is to take the generic 2-point function of the Minkowski spacetime and evaluate and write here t of tau. Because t of tau is precisely this. This is t of tau, and this is x of tau. So I have to take that equation and just plug in the trajectory. So the same state, the same 2-point function, is only that is evaluated when the 2 points belong to the trajectory. So 1 over h bar 4 pi squared, and you know, we have all these a's that go out as a squared in the denominator, and there we have t1 minus t2, but t1 is this. I already put a in the denominator, sorry. And the trajectory, so maybe I should put here just 1, because the trajectory happened at the origin of coordinates for the Riller observer. So the trajectory For the regular guy, is tau 0, 0, 0, so it's just it's no reference. But this is t of tau, h of tau. So this is just sine, hyperbolic sine of a tau 1 hyperbolic sine of a tau 2 minus I epsilon squared plus, so all this is squared, plus the x is a hyperbolic cos of a tai 1 minus cos a tai 2 squared. Everything is in the denominator, the same line in the denominator. And if you manipulate this, you can take the squares and you can take the cos squares, and it is quite trivial to show that this goes to, in the numerator, 2 appears, and in the denominator we have just hyperbolic sine square of a over 2 tau 1 minus tau 2 minus I epsilon. So it simplifies a lot. I insist, we haven't changed the Minkowski, the vacuum state. We have the same state, the only thing is that we are evaluating
Is it A by 2?
a by 2 here, yes.
No, the denominator.
Yes, a by 2. A by 2 and a by 2 there. So before computing what I want to compute, let me make a remark on this 2-point function. So remember, tau 1 minus tau 2 is what we will call tau minus. You are right, my 2's and my tau's are too similar. So one remark, imagine that you are I am holding the detector, I'm accelerating, and I have this is the 2-point function of my trajectory. This 2-point function, so this 2-point function is periodic in imaginary time. In imaginary time. So if you take time minus to be complex, this is a sine, hyperbolic sine. So if I put an I there, it's like the sine, and the sine is periodic. So it's a quite characteristic 2-point function, and in fact, it is well known that 2-point functions, which are periodic in the imaginary time, are what people call thermal 2-point functions. This is like an aside comment. And the temperature of that thermal 2-point function is always given by, I think it's 2 pi over the period. So h bar, the period of the periodicity over Boltzmann constant, and the period here, if you compute the period that you have there with the coefficient 2 and the square also, you get a 2 pi over it. So if you show this 2-point function to a mathematician and you don't tell him where it's coming from, he will tell you. All physics you get from it is going to be like in a thermal state. The proof of this, or a proof of the relation between thermality and periodicity in the imaginary time, it's non-trivial. The first time I heard that, I was surprised. What the hell has periodicity in the imaginary time with thermality? It's not that difficult. I mean, it will take me 10 minutes. You can go to Wall's GR book, and in chapter on black holes, I don't remember if it's chapter 12 or chapter on black holes. Chapter. There is a proof which is just 3 or 4 lines. It's not that difficult. So if somebody who knows a lot of quantum field theory series is going to know the result a priori. But imagine that we don't. So I close the parenthetical remark, and I go back. I have my two-point function. I want to plug in the probability rates and compute. Before that, I know that what is going to matter as here, the only thing is that the two-point function is going to be now replaced by this. What is going to matter is the poles, the pole structure of the two-point function. You can see that the poles of that two-point function, the poles of, let me give a number, this 4. Are at, I call them labeled by n, are in the imaginary axis 2 pi over I over a n plus epsilon, where n can be positive or a negative integer. So it has infinitely many poles. Maybe I should have.
But how do you close sign H in the imaginary plane?
Sorry?
How do you close the loop?
I will
Okay.
go over that. I am just, before that, I am just telling you what are the poles of this function, and let's see how we use them.
Okay.
So this two-point function has poles in epsilon, and then you have to move in integer numbers like 2 pi over a plus epsilon, etc., and the same in the negative axis. So this is the pole structure, and somebody knows that this periodicity has to do with thermal effect. But we don't believe that guy, and we want to compute it. So I want to compute the excitation probability rate of an accelerated detector. So the maths are the same as before. Probability, also the two-point function only depends on on tau minus, the difference, so I can compute directly the probability per unit time. It's going to be given again h squared g m 1 2, the integral in the proper time, and e to the e1 e2 divided by h bar tau 1 times the two-point function. Hyperbolic sine square of a over 2 tau minus I epsilon plus. Exactly the same as before. This guy is negative, so I have to close on the bottom part. But the bottom part now is full of poles. Before we didn't, the result was 0, now it's full of poles. The only thing you have to do is compute the oranges of those poles.
I'm confused by that because doesn't sine H also go as an exponent of tau?
It's in the denominator, so.
In the denominator, so this is the part that really kills the integral when you go there.
Right, but if you have, doesn't it depend on the relative strength of A and the difference in the energies?
No, in principle not. So expand it, and you will see that this guy really dominates, and everything is given by the guy. I mean, this is periodic in the imaginary axis. So this doesn't go to infinity or minus infinity.
Oh,
When you go to
okay,
the
I
imaginary
see.
axis, this is just periodic. So it oscillates.
I see what you mean. Yeah,
So
okay.
it's not a real exponential that blows up. When you go in this direction, that is true if you go in those directions. But in that direction, that is just an oscillation, and that really kills the integral. Thank you for the question. So if you do the computation, just compute the residues, put them in Mathematica, and you get delta E, the right delta E over h bar 2 pi And I find this quite elegant. Just looking at the poles of the 2-point function, I can get all the probabilities of excitation and de-excitation of a detector. Always these kind of techniques of using complex numbers are quite amazing. And you obtain this result. Equal 5. And I want to put a box on it because it's quite remarkable. The first thing that is quite remarkable is that it's different from 0. Different from 0. The detector will get excited. Remember, same detector as before, Minkowski vacuum, no particles. The detector will get excited. And this is the probability rate that you are playing. So, conclusion, if A is different from 0, if A is 0, this is infinity, that was 0, the detector C particles. And we agreed in chapter 4 that the way that we define particles physically is if my detector C particles. So the state is not a vacuum. The detector will start beeping. So I will continue with this, but for me, this result is what tells you physically that the outflow effect is not an artifact, it's something real. The vacuum, the Minkowski vacuum for the accelerated guy is not the vacuum at all. It's full of particles. What I'm going to do right now is to extract the information about how many particles, because we see this number here, and it looks like something thermal, but I want to convince you that this is precisely what you obtain from a thermal spectrum, and not something else. So you have particles, and not only that, they are distributed thermally, and this is what I want to prove right now. But before, let me give you some questions. So the question I want to give you, as a homework, is the following. So this guy, you are accelerating, and this tells you that at some point you are going to detect a particle. So you are accelerating. Your interpretation is that the state is full of particles. What I am doing is just absorbing in my detector one Riller particle. It's full of Riller particles. I am just absorbing one of them. The question is how the inertial observer describes this process. He cannot agree because the state was empty. So he cannot see the process as the absorption of a particle because for him there are no particles. So question, how the inertial observer describes this process? Again, for the accelerated guy, it is clear. He sees a lot of particles around, he's just absorbing one. So for him, the state of the field was a state with n particles. His detector was in the ground state. He's observing that the final state is the Riller particles, is one less particle, and my detector is excited. So what I am asking is that the inertial version will be the following. For the inertial guy, the state is the vacuum. It doesn't have particles. I write here n, but really what I should write is u of r. This thermal state. I'm just telling you that it's full of particles, and I am absorbing one of them. And after that, the detector is excited. So what is the state for the quantum field? He cannot agree with that there is a particle less because he didn't have any. So my question is, what is that observation? It's a non-trivial question. The hint is go to chapter 5 where I derive this, because at the beginning of this derivation, to derive all these probabilities, I had the information of what the initial and final state for the field. And you will see that in the computation, the final state of the field is fixed, otherwise you get that zero answer. And you can read from that computation what is that. the answer is quite surprising.
So why would they both of them agree with the energy of the final state?
Yes, they agree in energy, of course. They agree in the Chomwin function, they agree in any unambiguous question. But when the question involves particles, it's your problem. This is my theory. When you can, in a curved space-time, avoid anything having to do with particles. Because
Yeah, but there won't be any problem. Like, he can have that 0m, right?
Sorry?
He can have this 0 and there, like vacuum means Minkowski's.
Here?
Yeah.
No, because then energy will not be conserved for him. Vacuum, and excited, where is the energy coming from? I mean, if you try to answer also that question is much.
Antiparticle,
Sorry?
vacuum plus an antiparticle of the particle.
But what is the antiparticle of a scalar field?
Particle itself.
Particle itself. Maybe that is the answer. If you try to answer the question of energy, that is much subtle. So don't try to explain what happens with energy conservation, because the energy is conserved, believe me, but it's much subtle. And so I'm not asking you to resolve that question, because that's much subtle. But the question of what is this state is easy if you go back to where these formulas were originated and you see what the final state must be. And the answer is going to be on those lines.
So this x of tau written in terms of sine hyperbolic, isn't these the coordinates of the accelerated observer as seen from an inertial field?
Yes, yeah, this is
Because
T
in the
of
form
tau.
of the particle you would just have tau 0, 0.
Exactly. This is T
So
of tau.
isn't what we have
X of
derived,
tau.
valid for an inertial observer looking at the
Of course, it doesn't matter who is looking at. What matters is that the detector gets excited, and that is an ambiguous question. You can have a detector here, this guy, and doesn't see anything. And
so this what we have derived is what an inertial observer
is the
looking
probability.
at
The probability of excitation doesn't matter who is. What is the probability of excitation of the detector, which is accelerated.
But we've done this analysis in an inertial field.
Right, but in the first case, the matter is not who is observing the detector. That is relevant.
But this is what you are asking.
Right.
That,
So
as if the inertial observer sees, what will he see the final state?
So the question is the following: I put the detector here. It's inertial, follows the inertial trajectory in space-time. It doesn't see anything. Now the detector is accelerating. He sees the sign. That is it. So it's not, maybe I was using the inappropriate words. Who sees that? When I say who sees it, because I imagine the inertial observer sitting with the detector in his lab and observing, and nothing happened. And the other is the accelerated observer, is moving with the detector, and a particle, another one, another one. So this is what it is. This is what the guy with the detector in his hands accelerating will see, and he will see particles all the time. Just let me do something, the last thing I want to do, just fast.
One question, the probability, if I remember, is per unit of time.
Per unit of time, this is what the dot means.
Okay.
Probability rate.
You have to normalize and
Right, because if it is on forever, it will diverge.
Yeah, exactly.
And this is just the question that you made the other day, And now is that your question is relevant. Is the detector on forever, or is only on for a while? You see that the probability per unit time is like a thermal state. So it doesn't matter how long it is on.
Will the observer
What
agree
happened?
that the detector detected something?
Yes, sure.
Okay.
You can see the atom is in the excited state. So you can do the same for the excitation of an accelerated observer. So now what I want to do is, what is the probability if the detector is excited to go to the ground state? And it's again the same interval in the tau minus e to the E2 minus E1, the tau minus divided h bar, and now the tubing function, h bar minus a over 2 square hyperbolic sine square of the now what I have to do is to close the loop on the top because the exponent is positive. So I pick, remember that the pole that is at the origin normally is shifted to I epsilon. So I pick all the poles that corresponds to n equal 1, n equal 2, n equal 3, which are identical to the n minus 1, minus 2, minus 3. But in addition, I am picking now the pole in the origin. That before I didn't pick that because it is shifted. So I don't get the same answer. I get the same answer plus the contribution of the pole of the origin. Maybe I should write it in a separate way. Let me write it together and then separate. 1 over h bar squared. Can you guess? Well, I want to write it separate, the contribution of all these poles. And that is going to be equal to the contribution of all these poles. So the same answer. Plus a new contribution. Can you physically interpret the two cases?
It's the spontaneous.
Exactly. The spontaneous and the stimulated. Of course, the excitation is always stimulated, cannot be spontaneous. But the excitation can be spontaneous and stimulated. So if you do this, you will get the total probability of the excitation, which contains both delta E. I am writing delta E is positive, is E2 minus E1. E2 pi over A delta E over H minus 1. And this is the same as the sum of two terms, one which is exactly the same as equation 5. I don't do it, but if you compute only those residues, you get the same as equation 5. So this is from poles with n larger than 0, plus something identical to what we compute for the Minkowski spontaneous emission. Just repeating delta E over 2 pi h bar. So this is pole n equals 0. And as I said, the physical interpretation is that this is stimulated or induced emission. This is spontaneous emission. Of course, the spontaneous emission doesn't depend on how the detector is moving because it just has to do with the detector itself. So just to finish, let's discuss over this result. This is the result I wanted to obtain mathematically. I wanted to do it in some detail or in full detail if you want. Because I think it's quite interesting and and really completes the mathematical interpretation of all the times I have said that the notion of particles are ambiguous. This is an example in which the same detector will see different things depending on the state of motion. And this is telling to us that the guy, you have the detector accelerating. For that state of motion, the state is full of particles. And this is the probability of the de-excitation, and that is the probability of excitation. and this is, I mean, Unruh did something like that, maybe not, it's a bit more in detail, but this is what really convinced people that this Unruh effect is not a mathematical artifact, but it's really, it's really something that you will measure with a particle detector. So the last thing I want to tell you in the last 5 minutes is maybe summarize. I don't want to go over the details. I have the details here, but it's late. So it gives you a physical interpretation of this answer. So we know from the previous section, from the mathematical Fock representation, etc., that the state in the Rydler space really corresponds to a thermal state. Now we are observing these probabilities. Good, you be able to guess or to derive from these probabilities that the state that you are observing is a thermal state. So do you have any idea how to get from this number, how to infer from these numbers that the state is thermal?
From this exponential form, like 1 by e raised to the power something.
It looks like thermal, all these thermal factors are there, but there are many things which look like a tiger and are not tiger. There is a very nice argument. Let me just summarize it for you, and it's due to Einstein. So the question is, the question I want to answer is what these two probabilities we have computed tell us about the state of the field. And the argument goes back to Einstein. I'm sure you have studied these Einstein coefficients. Einstein was studying a set of atoms in equilibrium with radiation, and he was saying that there is some probability of excitation, and that is proportional to some coefficient, one of the Einstein coefficients, times the density, the particle density of radiation. He was thinking about photons and an atom in some place. He also defined the probability of de-excitation, and he said that you have two parts. One is stimulated or induced plus spontaneous, which doesn't depend on the. This is the particle density of radiation with frequency omega, and omega has to be equal to the energy of the gap of your detector or your atom. These B and A are Einstein coefficients. He derived that this guy has to be the same as this guy, and this is precisely what we have obtained. The stimulated excitation and de-excitations are exactly the same, and here in addition we have the induced. And he was able to derive, it's not difficult to realize that that if you impose thermal equilibrium, so at thermal equilibrium, if the ratio between these two guys is something in particular, you can induce that this U is thermal, that this U follows the Planck law of a black body spectrum. So he told us what we call now the detailed balance principle. This is in any book that you want to find, and let me give you the result. I am not deriving this. Just using thermal equilibrium and the Boltzmann law of distribution, he was able to derive that if this is equal to e to the minus h bar kb t, where t is a number, then radiation is in a thermal spectrum at temperature T. So looking just your detector, you can infer that the environment is thermal. Just looking what is the ratio of probabilities. And the arguments are just thermodynamics, just imposing using Boltzmann distribution and equilibrium. So we can use this principle to see if our ratios satisfy that. If our ratios satisfy something similar, we can A, induce that the state is like a thermal state, and T, read the temperature. And as you can imagine, this is satisfied.
So that means that if I choose any other state that is not thermal, that relation is not going to be.
It's not going to be true. So you can induce the thermality of the environment just looking at the probability distribution of your excitation by the excitation. So if you take our 5 and 6, I mean, for us, this is not really a surprise because we have seen in many other ways that the state is thermal, but I think it's quite nice and really closes completely the argument using particle detector. You obtain that this is 2 pi over A delta A over H. So, therefore, the detector observes stuff as if it was inside an oven at temperature, the room temperature. And this is again what we call the celebrated and remarkable Unruh effect.
So you're missing a minus on the
Here. Thank you. So 2 comments and finish. First of all, just in words, for me, this closes one for all the discussion of particles. I will try to avoid particles in general. I will try to compute everything using unambiguous quantities like the energy momentum tensor, 2-point function. All observers will agree on that. They are, it's like the distance between 2 events, the interval between 2 events in general relativity. Every observer, regardless the coordinates that you use, they will agree on that. The same with n-point functions, etc. And whenever you have some preferred notion of particle, maybe it's useful and you can use it to build some intuition, but in general that is not available. And the last question is how difficult is to measure this? To observe this? There are many proposals, and I have here more stuff to say, but just to summarize, if you put units, the Unruh temperature is the acceleration, 10 to the minus 19 Kelvin, when the acceleration is in meters per second square. So in order to get 1 Kelvin, you need an acceleration of 10 to the 19 meters per second square. That is a pretty big acceleration. That is the main difficulty. People have tried different things. First, to see that directly with the smart experiments. That is quite difficult. Second, to explain some phenomena that we see in nature and we don't know how to explain using the Unruh effect. You see something which is weird, and you say this is because that a particle in ice cube, a neutrino that enters the ice and decelerates. For that, the neutrino is decelerating. He's going to see a bath of radiation. He's going to interact with radiation. His decaying rate may change because the environment, and there are many things like that that are not conclusive. Nobody claims that there is no agreement that has been observed. That's the way it is. As I said, some prominent people really believe that you don't even, if you believe in quantum field theory, this is true. Period. It would be nice to see it, but there is no additional speculation here. There is no single ingredient that we have added to our theory. In the previous derivation, in my interior, because the 2 representations are inequivalent, we can discuss, and you don't have mathematically clean stuff. But this is more physical, so many people believe that this is just a prediction of quantum field theory in core space. Not even that in flat space. So my goal with this is show to you a physical example in Minkowski spacetime, in the simplest spacetime that we can imagine, in which this ambiguity, the notion of particle is just right in front of you and you cannot avoid. So I hope this closes the discussion about particles and their nature once for all. And from now we will do field theory, which is perfectly well defined and unambiguous.
So if this can happen in flat space-time, that means this happens in QFT in flat space-time, right?
This is QFT in flat spacetime.
Yeah.
QFT
So
in flat
can they
spacetime.
not see this in LHC because that's what they do?
No, but you know,
But how come, like, why is it a surprise if it happens in flat space-time? Like, so, like, why is it associated with QFT in curved space-time? It's
I mean, no, you can say that this is no. So because in QFT, in flat space-time is because you are choosing somebody would say very weird observer, non-inertial observer. You know why you are using that. You know the natural observers in flat space-times are inertial. The point is that in curved space-times you cannot avoid that. There are no inertial observers, so the question is even stronger. So the point is that to show to you how obvious or how what happens in curved space-time, in flat space-time you can also show the same effect using accelerated observer. But this is an effect of quantum field theory. I could not say that it's on curved space-time. Quantum field theory. The notion, what you mean by particle, is ambiguous and is basis dependent.
For the homework, is that a massless particle?
Yes, it's a massless particle.
Okay.
Doesn't matter to match, but it's a massless particle. It's just to show you, you know, how different the two observers describe the same physical effect. Any question?
If E1 is changed to E2, then the inertial observer can say that since the detector is accelerating, so its energy is increasing anyway. So E1 can change to E2 without having an effect on
the energy discussion is quite complicated. So you're right. You know, one has to see who pulls the detector, how much energy. So and the final answer is quite complicated. The final answer is in a paper by Wolf and Unruh that you can read. The two together, and you know it's quite nice and it's quite subtle. But to answer, you know, and they discuss energy, you know, causality, but my question is simple. My question is, what should I write here? You can also read that paper, you know, it's for curiosity, to see all things, what happens with energy, what happens with causality. But I am just asking, what do I write here? And this guy, I have to write a state in Minkowski fog space. So I write the vacuum, one particle, two particles. What do I write? And the hint, remember, go to chapter 5 and see how I derive all these probabilities from the very beginning, and you will see the final state, what must be to have a non-zero answer. Any other problem? This closes the chapter, Hawking radiation. Let's say.